Alright guys, welcome to video number 2 about substitution and elimination reactions. So this video is going to be covering leaving groups, okay? Remember I was using stuff like Br and Cl and chlorine in the last video showing all the mechanisms, right? And I was referring them to them as leaving groups, right? Because they left. So I'm going to talk more about what the leaving group is, right? Because you will encounter questions where they will ask you to rank essentially what is the better leaving group or something like that, or a question that makes you need to think about that. All right, so let's get to the general idea here. From you will see me in the future talk about nucleophiles, and instead of writing the full word, I will write NU with a lone pair and maybe a negative charge. Okay, remember nucleophiles are just doing the attacking. Okay, so let's change the color actually of this so that we can organize our stuff a little better. So I have this nucleophile here reacting with R. Any R group, doesn't matter. LG. Remember, LG is the abbreviation for a leaving group. So the general mechanism, remember, of the leaving group is just kind of like this. Now this isn't particular to anything in terms of SN1, SN2, E1, E2. I just want you guys to have a general idea of what the leaving group does. So we would have now the nucleophile bound to the R group, and the leaving group gets kicked out with its negative charge. Okay, so the leaving group leaves. So what makes a good leaving group? Okay, all these substitution and elimination reactions require that the leaving group leaves. All right, now it is better for these reactions if you will get a higher probability of these reactions occurring if your leaving group, if you have a good leaving group, right? But what does it mean to be a good leaving group, right? How would you know what this means? So I want you guys to think of this. We have our leaving group is attached to our R group, whatever, some alkyl group. In the reaction, our leaving group will end up leaving and getting a negative charge, right? Will it be more likely to react if the resulting if the resulting leaving group right here, this free leaving group, is more stable, or if it becomes unstable in this process? Okay, so I went from stable to stable, or stable, unstable, right? Think about it. It's much more likely for this, right? It doesn't, if it's stable already and when it leaves, it becomes unstable, well, then what's the point, right? It's going to think, well, I'm not going to do this. I'm just going to go back, right? So a good leaving group is something that will be stable when it is like removed, when it actually has left, all right? So keep that in your head. So in the previous example I talked about, I used chlorine and bromine, all right? Well, you got to think back to Ario. Chlorine, I had something like this, right? And when it left, I got Cl minus, right? Think of Ario, right? Chlorine, it's pretty electronegative, right? But it's pretty big as well. I mean, it's bigger. So it's because on the second row, third row of the periodic table. So it's pretty big. So it can spread out that negative charge in its electrons over a fairly wide distance, right? Thereby being pretty stable when it's free. So the halogens are good leaving groups. Bromine is the same thing, but it can spread it out even bigger distances than chlorine, Br minus. So it's even a better leaving group than chlorine. Iodine, same thing. Iodine is the bigger one of all of them, and so it'll spread it out over a bigger region. So it's even a better leaving group than chlorine and bromine. But what about fluorine? Fluorine is the most electronegative atom, and it's also extremely small. So now you have your negative charge, your chlorine, so your electrons and your fluorine concentrated in a really small area, right? Remember that like charges repel, so you have a lot of electrons all clumped together. So they're going to try to repel each other. So this fluorine isn't that stable like this. So it'll much rather prefer to remain bound to whatever it is than to be F minus, okay? So you can see that our leaving group ability with halogens is better as we move down the column, all right? So definitely think of that, all right? And fluorine is not a good leaving group in general, okay? So what else constitutes a good leaving group, right? So let me just erase this stuff. All right, well, what else constitutes a good leaving group? Well, how about this example, okay? Now, you don't have to know what reaction this is going to be, nor do I expect you at this point, having only watched the first video, to know at all what the next reaction, out of the four, which of these reactions is going to be. I just want you to think about the OH. We know that all four of the reactions, SN1, SN2, E1, E2, requires that a leaving group leaves, right? That's where it gets named from. So the general mechanism I could just write, obviously not knowing what this reaction is that the OH just leaves at one point. So we know it'll get a negative charge, right? Well, where have we seen OH minus before? How about NaOH, right? But you know NaOH from Gen Chem and now, you know that it's a really strong base. You know that if I put it in, when I put it in water or something, you get Na plus, which doesn't really do anything, and OH minus, a super strong base. Well, think of it this way. A strong base is going to react really quickly, right? So that means it's more reactive as OH minus than it would be right now. More reactive means unstable, okay? So that means as OH minus, more unstable than it would be bound to the carbon chain, right? Which means if it becomes more unstable, we can then say that that OH is a bad leaving group, okay? OH is not a good leaving group, right? And we can use the same logic to think about the other ones. So here we had, actually, no, I'm not going to say that. I was thinking of something else, sorry. So OH isn't a good leaving group. Now, there is a way to make it a good leaving group. If I added an acid like HCl, we know that, here, let me draw the bonds. We know that OHs or alcohol groups are relatively basic. O would grab the H, and now we get O, H, and then another H, so a plus charge. Now, obviously not knowing what kind of reaction this would be, imagine this leaving group now leaves. I get H2O. We know H2O is just water. We know water is stable, otherwise we'd have a lot of problems if we were drinking something that's an unstable compound, okay? So now it is a much better leaving group because I added acid, and so you'll see that in the future. That's one way to make an alcohol a good leaving group, by turning it into the conjugate acid. There are other ways though, but I will not be saying them in this video. All right, and so that's one way we can turn alcohols into a good leaving group. And so that's the general idea of leaving groups, all right? Just think of REO, okay? So think about it that way. We know that the halogens are relatively stable with the negative charges. And we know that the further down in the column we go, the larger they get, so they can spread out the negative charges over a larger distance, which is even better, right? Whereas fluorine, the most electronegative atom, right? And it's small on top of that, well, that's going to be a lot of negative charges concentrated in a really small space. And because the like charges repel, those negative charges are going to repel. That fluorine is not stable. So we can think of our leaving group ability as going down the column for halogens. So it would be chlorine, bromine, iodine. So leaving group is better going down. Okay. So they will ask you questions maybe to order this and like what's the better leaving group or something like that, something similar to that. Okay, so that's a little quick thing on leaving groups. In the next video, we're going to be covering what some of the nucleophiles and bases are. All right, you have to. That next video is going to be extremely important because it's going to be the basis for determining a lot of the reactions in terms of how to decide whether a reaction goes through SN1, SN2, E1, or E2. All right. So if anything here is a little bit confusing, please don't hesitate to email me. If you're watching this on YouTube, leave a comment so that others with the same question can also get it answered. Go to the CLC or office hours, and I will see you guys in the next video.